and this is my end of chapter 9 presentation for math for 12 differential equations at Mayfield State University. This is for spring 2023, and my chosen topic is the logistic model of population growth. Okay, so why am I motivated to do this presentation? Well, first of all, we started this chapter from exponential growth. And my question at the time was really, and you can see from this representation here, if we really believed in exponential growth in terms of population, that means that there's no limit and it's very unbelievable. But then after that, we learned a few models which involve some limitation, and one of them is the logistic model. And you can see from here, this is the simplified version. It shows you that, well, there is a carrying capacity. And this is the more mathematical model. It shows you that we can actually track the initial value of the population, and then we can come up with this formula to calculate, to find the carrying capacity, and to predict at any time in this timeline, we can find the population. So anyways, I found a interesting discussion over here on this website to talk about different types of models to predict population growth or decay. So I included here. So this is my chosen problem, and I found it from here on this website. And the problem says the spread of flu in a certain school is given by the formula here, where T is the number of days after students are first exposed to infected students. By the way, there's a typo and I couldn't fix that. Anyways, based on the given information, we're asked to find answers to the following three questions. A. The formula is a solution of a logistic differential equations. Identify the values of both the constant K and the carrying capacity. B. Find P of 0. Explain its meaning in the context of the problem. C. How many days will it take for a total of 400 students to become infected? Show all your work. Okay, so let's get started. To answer part A, I write the given formula and the formula we have for logistic model from the textbook here, side by side, and then I compare the corresponding coefficients and variables. So the yellow part, that's the M, that's the carrying capacity. In this model, that's 2100. And the green part, that's the A, here is e to the 4.3 power. And then here, the pink part, this is e to the negative kt. Here we have e to the negative t. So then I identify k as negative 1. And the carrying capacity n, that's 2100. And A here, it's about 73.4. So that's A. So part B asked us to find P of 0 and explain the meaning in this context. So I plug in the formula, the function into GeoGebra, into the graphing calculator, but I changed P of t to f of x, and also I specify x should be greater than or equal to 0 because x here, or t in the problem, that represent the number of days. So here's the model. And then I plug in f of 0, and I found here p of 0 should be about 28.1. This means that about 28 students were infected by the flu on the first day of the spread. So that's part B. Okay, here is part C. So we're asked to find the days it will take for a total of 400 students to be infected. And again, I use graphing calculator in GeoGebra, and I create another function g of x equals 400, and then I track the intersection between f of x and g of x, and this is what I find, the intersection point. So then you can see from here that P of t, when it's equal to 400, t would be around 2.853 days. So this is my conclusion. It would take 2.853 days, less than 3 days, for a total of 400 students to be infected according to this model, if nothing is done to slow down or to stop the spread. But again, is it really realistic that so many people will be infected within just 3 days? Well, still I doubt it, but that's a conclusion that I found according to this model. So this is the end of my presentation. Thank you for listening.